function if we graph its derivative. And if you think about when we write the equation for a derivative just in terms of x, you just get another equation, and there's certain characteristics that are really, really important for us. And so today's kind of our, baby steps into this, and we'll keep coming back to this over and over again. But it says, because we can think of a derivative at a point in a graphical terms as slope, we can get a good idea of what the graph of the function f prime looks like by just estimating the slopes. Works out really nice if the slopes are linear, because you can really graph those. But we can at least estimate it. And so I kind of took this page from your book. So the next slide, I can't hide it from you. It's already there. But try not to get too far ahead of me on this. But this is the function itself, okay? So this first one is the function. So maybe you want to label this as f of x. And there's certain things that we should be able to tell about this function's derivative by just looking at it. Because you see how this line, would you agree that this line is increasing? If I drew in my slope, like maybe at B, if I drew in my slope line, is that slope going to be positive or negative? Because that line's going up, right? What about on this part of the line? Would you agree that this part of my line is decreasing? And notice if I pick any point, they pick this point D here, but if you pick any point along where it's decreasing, and you draw in your slope, which remember is just the line tangent to it, what do you notice about that slope? It's negative. It may actually estimate the slope to be 1 and -1. I don't feel like we're there yet to estimate the actual slopes. But you can definitely tell it's positive, it's negative. What about right there at C? How would you classify, not about slope, but what would you call that point C on this graph? What? A turning point, right? And even more specific of this one, we could say it's a maximum, right? Because it's like the turning point where it changes from increasing to decreasing. What if I drew in the slope of that one? What's the slope of that line? 0, right? And so we talked about in last chapter, a lot of the times it said, find where the slope has the horizontal tangent. Notice where it's a turning point, it's always going to have a slope of 0. Look, if we come back down here to F, is that another turning point? Look at the slope of it. Also 0. And so some certain things to notice about that. And so they actually sketched the slope itself. So we could label this, they did already, but I'm going to label it down here, as f prime of x. And notice, they actually sketched this. We're not doing much of that today in terms of curves. But notice from A to C, right? From A to C, what could you tell me about the original graph from A to C? It was increasing, and what do you notice about all the y values from A to C? Do you agree that they're all positive? Which means it's all positive slope? Maybe if we jump down here, I'm going to skip this one. What is happening when the function is increasing? We could say the slopes are greater than 0, or the slopes are positive. What else does that mean in terms of our graph? If the slopes are positive on the derivative, that means it's going to be positive numbers. So I'm going to say f prime of x, that's the derivative, is above the x-axis, because those are all positive numbers. And again, if you skip over here to after f, it changes back to increasing, and notice after f, it goes back to positive numbers. And look at what happens when the function is decreasing. From C to F, those are all decreasing values, which means we already figured out that means the slopes are negative. So slopes are less than 0. So what does that mean for my graph? When the slope is less than 0 on my derivative graph, look at the y values. They are less than 0. So I'm going to put f prime of x is below the x-axis. What's happening when the derivative is 0, or when the slope is 0, On this graph, what happens when the slope is 0? Those occur where? At the turning point. So what is happening when f prime is 0? We can say on f of x, it means that it is at a turning point. More specifically, we could say that's a max or min of my graph. What happens on this function? When the slope is 0, how does that look on my derivative function? Where are my slopes 0? At what letters? C and F. Over here. C and F. Where do those end up on my derivative graph? Yeah, those are zeros of the function, or x-intercepts. So we could say on f prime of x, if the slope is 0, it's a 0, right? Like if you're just graphing the slopes. So I'm going to put a 0, which is the same as saying an x-intercept. Eventually, we're going to get to the point that we can sketch our own derivative graph like that, but we're not quite there yet. We can do some linear ones, but today the big idea is matching up original functions with the graph of its derivative based on this fact. If the slope is positive, that means the function was increasing. If the slope is negative, that means the function is decreasing. And at max and mins, they show up as zeros on the function. So if you turn the page, I think I have some lovely matching for you. Oh, what? So I've given 3 functions here, and then I've given 6 derivatives. So these are the derivatives, these are the original functions. We want to match them up. So I want to kind of show you the thought process that I have when I do this, and then I have 3 more that you're going to do on your own. So for me, the first thing that I do is I find where the zeros of the derivative are going to be. And where do the zeros show up on the derivative? At the turning points, when the slope is 0. So on this one, since it has a turning point right here, I know that my derivative is going to have to cross at 0. Because the slope is 0, right? So I'm kind of drawing in my slope graph on top of this one, okay? And then look to the left and look to the right of each 0 and figure out whether your function's increasing or decreasing to determine whether the slopes are positive or negative. So on this one, what's happening to the left of my turning point? This graph is decreasing, which means the slope has to be negative, has to be below the x-axis. So just kind of roughly speaking, it's got to be below here, right? So I'm just going to kind of, I don't know, right below, maybe just, I want to just draw a line because I know what it's supposed to look like. So I'm just going to write below over here. And on this side, what do you notice about this graph? Increasing. So if I drew my tangent lines in, no matter where I drew them, they would all have a positive slope, which means that my derivative would have to be above the x-axis. So look at our 6 choices and find one that has a 0 at 0, and to the left of that is below, and to the right of that is above. This one doesn't have a 0 at 0. Not good. This one doesn't have a 0 at 0. This one doesn't. Yeah, the only one that has a 0 at 0 is B, so you don't even need the other parts on this one. But this does fit. Do you agree that this is showing me negative slopes? Right? I'm not looking at the slope of the line. I'm looking at the y values. This is below the x-axis. This is above the x-axis. So that means that for this parabola, the graph of its derivative would look like that linear line. So follow me on this. So now look at the second one here. How many zeros is our derivative going to have on this one? 2, because there's 2 turning points. And again, it always helps me. I like to print these out for you so you can kind of draw them in somewhere around in there and around in here. probably just based on that, you could probably pick the one that it goes with. But maybe not. Like, definitely A has 2 zeros, D has 2 zeros. But pay attention to your slopes, right? This is decreasing, which means it needs to be below the x-axis, and then it changes to increasing, so this would be below, and then this would be above, and then it's going to change back to decreasing and be below again. I think it has to be which one? D, because this one, look how far over the zeros are, right? Like it's not going to match to where those zeros are. Do you agree with that? But check it. It's below to the left of the zero, above in between the two zeros, and then below again. So D is the right answer. Any clue what I'm saying on this? Yes? What about number 3? Anybody got a guess on that one? It definitely has a turning point also, which means it's going to have a 0. And again, a lot of times you can tell just from the 0, right? Sean, what do you think? C, because this is my turning point, so I have to have a 0 up here around 3. And again, it's decreasing to the left, which means it should be below the x-axis, and then it changes to increasing, so that makes all positive slope values. And I think I agree with that. So I got 3 more on the next page. The same choices are at the bottom, but they're mixed up, so I just relabeled them all over again. So kind of, if you want to cross out the 3 that we've already used, you can, but they're not necessarily B, D, and C, I think. But I want to give you a few minutes and see if you can match them up, and we'll talk about maybe what happens there on the one that's this one. Like, why does that look so weird? But see if you can do those if you haven't already started of matching them up. Now, in your homework today, you have 4 of these that you're going to match the function with this derivative. Okay about this? I feel like, I don't know, 5 is an easy one for me because I can see these 2 turning points right here. So the only one left that has 2 zeros is B, but again, you can check decreasing, increasing, decreasing. So below, above, below. I think this one would be that B right there. Do you agree with that? Number 4 is kind of an interesting graph, and we'll talk about this a lot more later. Like, how do you know, like, where did this little hump come from in this? Well, because it has this weird little turn right there. But it only has one actual turning point. So it only has 1 0 right there. And notice that although it has this little twist here, that's still decreasing that entire time. Right? So although this is a little fancy down here, it's still all negative up to that 0. It's just some cool stuff happening there. But it is all negative, and then it changes to increasing past the 0. So E is the right answer. And for the most part today, this is what you're going to be dealing with in terms of polynomial functions. We're not going to get into it a lot. But look at 6. Number 6, we could actually write the equations for the derivatives because this is an absolute value function, but it's decreasing and then increasing, right? What would be the slope of this side of the line? Positive 1, because I could say up 1 over 1, up 1 over 1. And what would be the slope of this part of that graph? Yeah, so you actually, if the graph is linear, you can actually tell me the equation for the derivative. And so we're going to write this one out just so you can kind of see what it looks like. If I wanted to write the equation for this derivative, I'd have to write a piecewise function because there's two parts, there's two different slopes going on. So I'm going to write a piecewise function. And I'm going to start with the left side. This is just -1, right? It's just a number, no x involved. It's just -1. But you have to say, where is it -1? And do you agree that's just for less than 0? So I'm just going to say when x is less than 0. And then on this side, it's +1. And that's when x is greater than 0. And if you notice, the only one that we have left are just constant functions. To the left, it has a slope of -1. To the right, it has a slope of +1. And notice I didn't include 0 here. We're going to get into this with the next section of when does something have a derivative and when does something not have a derivative. But think about it in terms of limits. The limit of this derivative doesn't exist. Do you agree with that as 0? Because if I took the limit coming from the left, I'd have -1. The limit coming from the right, I'd have +1. So it doesn't exist, and we'll talk about why that happens later on. But that's why you just have a little, I don't know, kind of looks like a step function, but it's just a piecewise function. Okay, so that one would be letter D. And on your homework today, when they ask you to make your own derivatives, they should be straight lines like that. They're not going to make you do anything else right now because we're not there yet. Eventually we will be. So let's sketch our own graph here now that we did that one in our little introduction. Notice this one, they want you to sketch the graph of the function with these given things. So it says sketch the graph of a continuous function, which means they want it to not have any holes, gaps, asymptotes. They tell us this, f of 0 equals 1. What does that mean? It's just a point, right? This is just function notation. That's the same as saying when x equals 0, y equals 1, right? This is the x, this is the y. So they're going to use function notation when they give you points. They're not going to write it out when x equals 0, y equals 1. And then this is the calculus part of it. They're telling us the derivative when x is less than 2, when x is greater than 2. And notice the derivative is just a number, which means we can make this graph just a constant slope. The fact that they tell us it's continuous and the fact that they give us a point gives us a place to start. So I think we should start with the point that they give us. At 0, 1, make a point on your graph. At 0, 1. Just kidding. I even thought about it. I was like, see, I don't know.
I was like, that's not even like.
I don't know what I was doing. Oh, Lord. Sometimes I wonder how I can do calculus and then I can't even grab the point. 0, 1 sometimes. Oh, goodness. The other thing that's important is this right here. It's telling us where our derivative is going to switch from one to the other. So you don't necessarily have to draw this. If you want to, you could make like a little dotted line down at 2 just to remind yourself of, hey, my derivative stops here, but you don't have to. I'm going to on this one just so you can kind of see it. But on your homework, you don't necessarily have to. But just make sure you're aware your derivative stops at that point. So to the left of this, what is my derivative? When x is less than 2, my derivative is, that would be to the right. Right. When x is less than 2, my derivative is 2, right? You can't just make a line at 2 because of this point right here. But can we make, from this point, can we make it have a slope of 2? By just going rise 2, run 1? And I can do that. I can go rise 2, run 1. Rise 2, run 1. And then I'm just going to make a solid dot right there for now. Now to the right of this, what do we know our slope is? -1. You might say, well, how do I know where to make that slope of -1? It's continuous, which means where does the slope of -1 have to start? Can I start down here at -1? That would not be continuous anymore, right? I'd have a gap. Could I start here at -1? How do I have to start? On that dot, because it's continuous, which means it can't have a hole, it can't have a gap, it can't have anything. And from this point, can I make this side have a slope of -1? Yeah, that would be down 1 over +1, down 1 over +1. And really, if I go back and erase this, I've just made like a little piecewise function. And I can connect this like this, and this like this. And it kind of looks like absolute value, but it's really not, because the slopes are not the same on either side. But there's definitely some of that on your homework today. And remember, you're graphing slope. Derivative is slope, and so you can graph a slope when it's a linear or constant slope, I mean. Okay? Something else here that I think can be kind of tricky sometimes is talking about a one-sided derivative in the same idea as a one-sided limit, because a derivative is really a limit. But sometimes the derivative's not going to exist, and that's where we're going with this next section of how do we know when it doesn't exist. Well, one way to check that is through one-sided derivatives. And so there's lots of stuff here, but it says, it looks very similar to one-sided limits. It says a function is differentiable on a closed interval if it has a derivative at every interior point on the interval, and if the limits, as h approaches 0 from the right and h approaches 0 from the left, exist at the endpoints. Again, notice they're talking about if you're getting close to 0, if you're coming from the right, h is going to be a positive number. If you're getting closer and closer, but if you're coming from the left, you're actually going to be picking negative numbers, so they kind of explain that there. But here's kind of my little extra stuff here. A function has a derivative, which is a two-sided derivative, if and only if the right-hand and the left-hand derivatives are defined and equal the same value. So I want to show you what this means, because sometimes it's a little tricky when you're plugging it in. So let's see if we can do one, and I can make all this mumbo jumbo make sense. Why that's so blurry. Always sound like you're grumbling about something. I'm tired, I got. Alright, so using one-side derivatives show that the function f of x does not have a derivative at x equals 1. And so we're just going to do, notice it's a piecewise function, that's where we're going to come into play here. We're going to take the limit as h approaches 0 from the right of f of 1 plus h minus f of 1 all over h. Okay. And what we want to do is we want to compare that to the limit as h approaches 0 from the left, and I'm going to show you how that changes. You might say it doesn't change at all. Oh, I should have done the left first. Can we change this to minus? I wanted the left first because the right part is trickier. Left. Oh man, why did I pick a cubed one? So that would be 1 plus h cubed minus 1 all over h. Do you agree with that? Well, it's not so bad. If I plug 1 into here, 1 cubed is 1, right?
Yeah.
Okay. Sorry, I changed. Right. And then 1 plus h cubed, that's where you could FOIL it out like twice and do it again. You could use Pascal's triangle. But I'm just going to go from memory here and say that that's going to be 1 cubed And then it's 1, 3, 3, 1 is I think our numbers here. 1, so that would be plus 3h plus 3h squared plus h cubed. 1, 3, 3, 1. And then I have that minus 1 there tacked on. And the 1's cancel, and I get the limit as h approaches 0 from the left. I'm going to factor my h out, and I'm going to get 3 plus 3h plus h squared all over h. So when I plug in 0 in there, do you agree that I just get 3? I'm going to do the same thing as 0 comes to the right, and you might say, how's this going to change? Well, first time I did this, it took me a while to figure this out, but now I know how to tell you. Coming from the right means that I have to use the function on the right, okay? So that means instead of using this x cubed, I'm now going to use the bottom function when I do my f of 1 plus h minus f of 1 over h. But you got to be really careful on this, all right? So the 1 plus h, you definitely have to do the bottom function because you're coming from over there. So I get 3 times 1 plus h. But when I actually do f of 1, I'm asking for the actual y value there. Am I allowed to plug 1 into this bottom function based on the piecewise function here? So f of 1 actually goes back to what is the actual y value there, and we're not going to put 3 here. We're going to take the top function, and we have to plug it in because it's defined for 1 in the top half, and we would actually say that f of 1 is still just 1. It took me a long time to figure out that because the book example does not show where that came from. They just say the answer, and I was very confused. But it makes sense, right? You have to actually use where it's defined. So we get, what is this? 3 plus h, 3 plus 3h, minus 1. We get 2 plus 3h over h. Is that right? Well, like, I didn't just get it right away. Like, I did it, and I plugged 3 in here, and it worked out perfectly. Like, if you plug 3 in here, you get 3 equals 3, and I'm like, oh, it exists. Well, then I looked, and they said it didn't exist. They said the right and the left hand didn't exist, and so I had to go back and look and figure out, like, it took me a few minutes. Like, I just didn't get it right the first time I did it, because I didn't know, like, I plugged in 3 here. So then there's a problem here. Like, this doesn't work out so nice like up here, right? Like, if I try to plug 0 in here, I can't plug 0 in here. Do you agree with that? Which means we don't really have a way of doing this except for looking at a graph. And if we look at a graph of this, I think that if we keep plugging in numbers closer and closer to 0, we're going to get infinity or negative infinity out of this because there actually is a vertical asymptote of this graph. But basically, if you get something that doesn't work out nice, like it definitely doesn't equal 3, we can just say there's no limit because this side didn't work out so nicely. And so I think the directions here says show that the function does not have a derivative at x equals 1. So I do this work, and then I would say the limit as h approaches 0 from the left of this function does not equal the limit as h approaches 0 from the right of that function. So no derivative exists at x. Or you could say the left and right hand derivatives don't exist. I just didn't want to write all that out, so I kind of just wrote the limit part. that's just pay attention to that, because it's really easy to think about, I'm at the second half of the piecewise function, I want to use that the whole time, but you just have to pay attention. I think there's one on your homework like that, to just kind of watch out for. Right? And it could exist, but it might not. I think that's it. There are some questions on your homework today. This is 3-1, day 2. There's some like story problem questions today where they ask about things like, when is it the coldest? And there might be one about rabbits, like when is the number of rabbits increasing the fastest? It's all about slopes today, so we'll definitely talk about some of those tomorrow, but think about them. Like look at the graph and think about, oh, when it's the steepest, it's going to be increasing the fastest if that's the slope, or where the slope is 0 is such things. So think about those. Definitely there's some odd ones. You can look in the back of the book to see where they got it from. But just try them. Don't just leave them blank. It's kind of a frustrating assignment for some people because it definitely isn't just, like day 1 was just plugging in numbers, limits over and over again. Day 2 is more applying the idea of derivatives to story problems. So, yeah, like there's a question that says, on what date is the amount of daylight increasing the fastest? They're talking about slope there. And so make sure you find the graph that goes with those, and we'll talk about a couple of those on tomorrow. Because you're plugging in F1, so you have to plug in the actual value of F1, not what it could be. Like it's approaching 1 this way, but it isn't defined F1. So when you actually do F1, you have to plug it into the one where it's defined. You know what I'm saying? Like it's not supposed to. It's not. No, it is defined because this includes 1 and this one doesn't. So it's not. Yeah. So like you always put it in the one